Morning, everyone. So it's been a few days since my last lecture. So in the interim, I've put up a corrected version of the lecture notes on my webpage. I've just reminded you of the right place to go at the top there. So in particular, I think I have now finally sorted out the slightly dubious proof of theorem 4.14. And I've had a couple of requests to go through the new version. So I thought I would do that after dinner this evening. So immediately after the meal, I think probably by 8:30 or so we'll be finished. So the room is free at that point. Anybody who would like to come and watch me sort of talk my way through it is most welcome. There's absolutely no pressure. I know everybody's quite tired by now, so don't worry about that if not. It's all in the notes if you want to read it. Go ahead. There is also a lecture tomorrow, but I've got a lot that I want to get through. So I didn't want to come back and sort of redo material that I've already done in the formal lectures. Okay, so let me remind you of where we got to at the end of the last lecture. So we were studying GNS, which is a uniform random connected graph with vertices labelled by n and with surplus s greater than or equal to 1. So remember that means n plus s minus 1 edges. Okay, and we saw the proof of the theorem that this thing has a scaling limit. If I do the same distance rescaling that I do in the context of a bien-aimé tree with critical offspring distribution, finite variance, conditioned to have total size n. So we get convergence of the distribution to this limit space, which we obtain first by taking an R tree coded by the excursion E tilde s, where E tilde s has this absolute continuity relation with the normalized Brownian excursion. So I'm just reweighting its law in favor of excursions that have slightly bigger area. Okay, so then I take the R tree that's encoded by actually twice E tilde s for the same reason that I'm using the 2 times it in the Brownian case. Then what do I want to do? I want to find supplementarily, so S pairs of vertices or S pairs of points xi, yi, which are uniform in the area under this excursion. So let me draw a little picture. I've got my excursion, and I'm just finding S pairs of points uniformly in the area under that excursion. And then for each, I've got an x-coordinate and a y-coordinate. So let's say x1, y1 here. Sorry, this is probably completely invisible at the back. Okay, so what do you want to do? You want to look rightwards until such a time as you hit the excursion again, and that identifies an z1 that goes with x1 and y1. Okay? And then what I want to do is I want to identify pairs of points, so S pairs of them, under this excursion, which are given by the projection on the tree of the point xi and the point zi. Okay? And those vertex identifications are going to be what gives you the cycles that you inevitably have in a graph of positive surplus. Okay, so that's where we got to at the end of last time. And I want to now make use of this result in the context of the critical Ödel-Renyi random graph. So that's the next chapter in the notes. So I expect lots of people have come across this model before, but I'm not going to assume that. So let me first say, not least because there are 2 different random graphs which get referred to as the Ödel-Renyi random graph, let me define what I mean. So I'm going to be talking about the model which is often called GNP. It's actually simultaneously introduced by Gilbert independently. So here we have the vertex set, again labelled by the natural numbers 1 up to n. Okay, so that means that there are n choose 2 possible edges that I might include in this graph, and I'm going to do the simplest thing imaginable. I'm just going to include each possible edge independently with probability p and not otherwise. So an edge is now a pair of vertices which, let's say, I and j, such that I and j are different. Okay, so independently, so let me say I not equal to j, independently with probability p. Okay, so in this context, the total number of edges here is going to be binomial with the first parameter being n choose 2 and the second being p. Okay? And what I'd like to look at is the sparse regime where we have nice bounded vertex degrees. Well, not bounded, but nice tight vertex degrees. Okay, so in particular, I'm going to focus on the regime where p is a constant divided by n. Okay, so let's just quickly think about what the degree of a specific vertex in my graph is then distributed as. So I've got n minus 1 possible neighbours, each of which is present with probability c on n. Okay, so on average I'm getting c-ish neighbours as long as n is large. Okay. So I'm thinking about c here as being a constant. Okay, and so the degree of a fixed vertex is distributed as binomial, so n minus 1 c on n. And I want to be thinking of this for large n as being approximately Poisson c. Okay, and that's an approximation that we're going to make quite a lot of use of in what comes. Okay, so let me write down the sort of theorem that gets referred to as the emergence of the giant component. So let me write, so gn1, gn2, and so on, for the components of this graph. Okay, so in general it's going to have many different connected components, and I want to write that for the components of the graph listed in decreasing order of size. Okay, so there's no reason why two of these components can't have the same size in principle. Okay, and so in that case, just break ties arbitrarily. I'm quite often going to use the rule that whenever I've got a choice, I'm going to take the component that has the smallest, lowest labeled vertex first, for example. But it doesn't need to be that rule. Okay, so ties broken arbitrarily. Okay, so then the sort of theorem which is due to addition-Rényi, this is theorem 7.1 in the notes, is that if I look at a value of c which is strictly less than 1, then the size of the largest component is OP of log n. Right, so it's tight on the order of log n, okay? Whereas if I take a value of c which is bigger than 1, then, well, this is true for the second largest component, but on the other hand, the largest one actually has a limit in probability when I rescale it by n. And this limit in probability, so where theta of c is the strictly positive solution to a particular equation, which is the following. So theta equals 1 minus e to the minus c theta. And I'm going to try and explain why this is true in a moment. But let me first say what this is saying, sort of broad brush. So this is saying that for c strictly less than 1, all of the components are microscopic. None of them contains a positive proportion of all of the vertices in the graph. Whereas if c is bigger than 1, then the largest component does indeed contain a proportion of the vertices, indeed a proportion which converges in probability as n goes to infinity. Okay? So for c strictly bigger than 1, this is a strictly positive quantity. Okay? And on the other hand, all of the other components are again microscopic in the same sense that I had in the subcritical regime. Okay, so this is a phase transition with its critical point being at c equals 1. Okay, So this is known as the emergence of the giant component. Where, hopefully, obviously, this is the giant in the supercritical regime. Okay, so there's a deep connection between this result and the branching process phase transition that I talked about in the beginning of the chapter on bien-aimé trees. And I want to sort of talk through the heuristic for why that's the case. Okay, so I'm not going to write very much. I'm just going to sort of try and talk through this. So imagine doing one of our explorations that we've been doing. Let me start from some vertex somewhere in the graph. May as well be the vertex 1. Okay, and let me think about the size of the component in which it's contained. Okay, so we've just seen that 1 has a binomial n-1 C on n number of neighbours. Okay? I don't really care about their labels, except in as much as let me explore next from the lowest labelled of those, just to do something definite. Okay, I suppose that's this one. Okay, so how many neighbours has it got? Well, this was some random quantity, let's say capital N. Okay, so this guy might connect to these guys, and that would be surplus edges in the way that we've seen before. But I'm really interested in how many new connections does it have. Okay, and the number of new connections it has is again a binomial random variable, except I need to exclude now everything that I've got on the board from the possible space of things that I might connect to. And so I think, assuming I haven't done my calculation wrong, that gives me bin n minus capital N minus 1, but again C on n, because each of the edges is independently present with probability C on n. And so as long as this big N here is small compared to little n, then roughly again, I've got a sort of Poisson number of offspring with parameter C, roughly. Okay, so I've got some Poisson number of offspring here. Okay, so you can see that, at least morally speaking, if I look at this from a long way away, I'm essentially seeing something that looks like a Poisson C bien-aimé tree. Well, as long as I've not explored a macroscopic number of vertices, right? So the moment that I've explored order n vertices, obviously I'm going to start feeling it in this first parameter here. But until such a time as I do that, this is going to be nicely approximated by a branching process. Okay, so we have approximately a branching process with Poisson C offspring distribution. Okay, so one thing that we can say is that if C is strictly less than 1, this branching process is going to die out with probability 1. Okay, so I'm just going to get some little component. Okay, and then what am I going to do? Well, let's pick another vertex to start exploring from and go again. Okay, and again, I'm going to see something that's looking a little bit like a Poisson C branching process. And because all of these little branching processes that I'm setting off are kind of small in size, okay, that's corresponding to me only getting small components. Like I say, this is heuristic and it can be made rigorous, but I'm not going to do that right now because I'm going to do something a bit more delicate. So what about if C is strictly strictly greater than 1? Okay, so then there's positive probability. In fact, for a Poisson C branching process, this is precisely the probability of survival. Okay, so this is the probability of survival for a Poisson C branching process. Okay, so with that probability, this thing's going to take off. Okay, now necessarily, because the branching process on that event becomes infinite, this comparison is going to have to break down. I've only got n vertices available to me, so I clearly can't create an infinite component. But the point is that it's going to get very large, and that corresponds to me creating a giant component. And once I've created a giant component, if you look at what's left, so I've now got a number of vertices, which is n minus, so some, let's say, lambda times n. So then I'm looking essentially at a smaller version of my GNP, okay, where I've now got fewer vertices available to me and the same edge probability. Okay, and the point is that this will always end up being subcritical, the rest of what I'm looking at. So that's the reason why we're really only creating one giant component rather than multiple ones. Okay, so that was a bit hand-wavy. What I do next, hopefully, will be more precise. So let me just rub this off. Okay, so I haven't said anything about what's going on at c=1, and as is fairly typical, the most interesting but also most delicate behaviour is going on at the point of the phase transition. And that's really what I want to talk about in this lecture. So the most delicate behaviour is at c=1. Okay, and in fact, so I'm looking at a finite graph here, and so it's perhaps natural that there's not just one sort of critical value here, there's in fact a whole family of them. So that I'm going to refer to as the critical window. And it turns out that I'm going to have very similar behaviour for all values of p in this critical window. So this is the set of values p, which look like 1 on n, and then I can allow myself a little wiggle room, which is on the order of 1 on n to the 4/3. Okay, so this is going to turn out to be the interesting place to look for critical behaviour. Okay, so it turns out that in this regime, I don't just have one component that's on a different order of size from all the rest. I've got a sort of intermediate size scaling for a whole sequence of kind of largest components. So, the largest components have sizes on the order of n to the 2/3. And in fact, as we'll see in a moment, when I rescale their sizes by n to the 2/3 and I take a limit, I'm actually still getting some randomness in that limit. And that's another kind of signal of the phase transition. Here, if I rescale, I'm getting something deterministic out. Whereas at the point of the phase transition, when I rescale, I'm still getting some randomness going on in the limit. And that's sort of, there's some sort of statistical physics heuristics that say we should be getting that sort of behaviour at the point of phase transitions. Okay, so I've put in the notes an exercise which takes you through a sort of bare hands proof that the largest component must be OP of n to the 2/3, so tight on the order of n to the 2/3, to try to get you to start having an idea about how essentially the sort of tail probabilities for branching processes transfer into giving you size scalings for components in the random graph. So there's quite a nice kind of scaffolded exercise there, which I hope you'll like. Okay, so for the rest of this chapter, my aim really is to give a sort of quantitative comparison between what I would get if I were looking at a forest of Poisson 1 branching process trees and what I'm really getting in the critical Erdős-Rényi random graph. Okay, so let me do a bit of board cleaning, which could be a challenge because I think this thing is no longer sticking. Okay, so I want to start by thinking about sizes and surpluses of my components. Okay. Right, so let me think about putting myself at some point in the critical window. So I'm fixing this lambda and looking at my p being 1 on n plus lambda on m to the 4/3. Okay, so I keep saying a graph, but obviously I'm thinking about a sequence of graphs here indexed by n, and I'm going to sort of elide those two things all over the place. But just to be clear, I've got a sequence of graphs indexed by the number of vertices, and I'm thinking about taking limits along that sequence of graphs. Okay, so again, we've got gn1, gn2, and so on. The sizes of the components, the components listed in decreasing order of size. Okay, and I'm just going to use modulus signs for the sizes. Okay, let me have some notation for the associated surplus numbers, right? So each of these is a connected component, and it's got some surplus greater than or equal to 0. So let me list the surpluses in the same order as the components. So SN1, SN2, and so on. Okay, so there's no reason why those surpluses should themselves be in decreasing order. They're just the surpluses that go with those particular components. Okay, so then the theorem which is due to Aldous is that if I fix some lambda in R, then, and I'm going to hide the lambda from the notation simply because otherwise it's going to get very heavy to write down, but I'm fixing the lambda. So if I rescale these component sizes by this n to the 2/3, so I've got a whole sequence of components listed in decreasing order, and then as the second component of this object here, I'm going to think about the list of surplus numbers. So that pair of sequences converge in distribution to, well, some limit, which I'm going to write C1, C2, and this is going to be S1, S2, and so on. Okay, so I listed these in decreasing order, so these had better be in decreasing order. So this is some random sequence which is decreasing. So of non-negative random variables, numbers, so real numbers, such that the sum of their squares is finite, almost surely. Okay. And this S1, S2, and so on is a sequence of random non-negative integers. Okay, so I'm going to make these a bit more explicit in a moment, but let's first just think about what this theorem says. So this is saying that if I look at this critical point, or in the critical window, the component sizes are indeed on the order of n to the 2/3, and when I rescale, I'm getting random variables out in the limit. Okay, and then I've got some associated, so random natural numbers, which are giving me the associated surplus numbers with those components. Okay, so let me now give a description of what this limit object is. Okay, so before I do that, perhaps it would be good for me to say what the sense of this convergence is. So I've got a product between these two things. The first kind of sequence here is going to converge in L2. Okay, so that's one of the things that this is signaling, hopefully. No, so these are integers to start with, and they're integers to finish with. Okay, so I'm just really getting convergence here in the product sense. Okay, so they're really just 5, 3, 1, 2, 0, whatever. Okay, and they remain so in the limit. Okay, so this is good. So just to think back to what we were doing there, we were thinking about our surpluses being fixed numbers, right? So I want to eventually make use of that theorem, and that's good. These are, again, just, okay, they're random now, but they are just finite integers. Okay, so convergence for the first coordinate is in the space, so let's say L2 down arrow, which is just sequences X where the elements are non-negative and listed in decreasing order. So X1 is greater than or equal to X2, and so on. They're all non-negative, and we've got finite sum of squares. Okay, so that obviously I'm going to endow with its usual L2 distance. And it's with respect to the product topology in the second coordinate. Right, so how do we describe these limit sequences here? Well, I need a Brownian motion, or rather a Brownian motion with drift, in order to describe how to get to these two things here. So let me put some definitions here. So let's let W lambda of t be a standard Brownian motion plus lambda t minus t squared on 2. Okay. So this W here is a standard Brownian motion. Okay, and I'm just giving it this parabolic drift. Okay. So then what I want to do is think about reflecting that thing in its running infimum. So what do I mean by that? So I'm going to take W lambda of t, and I'm going to subtract off the infimum of values of the process between time 0 and t. Right, so what am I doing here? So I'm starting with this Brownian motion that's got a negative drift. So if you think about it, irrespective of the sign of lambda, eventually this term here is going to win, okay, and it's going to drag me down towards minus infinity. Right, so this thing has got quite a heavy drift negative. Okay, so then I'm going to pick out its minimum. Okay. Okay, so that's this decreasing process here. Okay, and then I'm going to kick the whole thing above the x-axis by just adding on minus the infimum. So what that gives me at the end of the day is a reflected process which is staying positive, comes back to 0 occasionally, but its excursions away from 0 are gradually getting shorter and shorter, because if you think what's happening to this process, it's getting pulled further and further negative, and so it's getting away less, if you see what I mean. Okay, so that eventually the t squared on 2 is winning.
The question about these different modes of convergence, does it kind of signify that the surpluses will be asymptotically independent, or is this why it's happening in the product topology?
No, so there's no independence between these two sequences, and in fact, if you maybe wait 5 minutes, I'll show you why they're in fact very dependent on one another. Okay. So
there's no like big meaning to the different modes of convergence?
No, so I mean, the important thing that I want to note here is that these guys aren't actually summable, but they're square summable. Okay, so, you know, this is a sort of non-trivial sense of convergence. Okay, right, so let's call that process R for reflected process. Okay, so now I want to add one little extra bit of structure, which is, I want to do something a little bit like what I did here with some uniform points under the excursion. So what I'm actually going to do is I'm going to say, let's take a Poisson point process in this upper quadrant, okay, and I'm just going to keep any points that fall under this function here and above the x-axis. Okay, so that gives me some random number of points in each excursion, maybe 0. Okay, and I've got, so this is going to be a Poisson point process in, so r plus squared, let's say r plus cross r plus, just to make it a bit clearer, of intensity 1, where we keep only the points which fall below this process. So this is r lambda of t. Right, so maybe it's easier for me to phrase this by thinking about what's the intensity of points in time as I'm going rightwards. And the point is I've got more chance of seeing a point, or higher intensity of seeing a point, when my process is further away from the x-axis. So effectively, if I project this down onto the time axis, what I'm seeing here is an inhomogeneous Poisson point process whose intensity is simply given by r lambda. So equivalently, so take, I'm going to call this p lambda, because that's going to be convenient for what happens later. So this is the process of points to be an inhomogeneous Poisson point process, or Poisson process of intensity. So r lambda t dt. Okay, so this has to be conditional, obviously, on this r lambda. Okay, so think about first sampling the process r lambda and then putting the Poisson point process on top of that, given the r lambda that we happen to sample. Okay, so then how can we describe these two things? So this is a process that has, obviously, excursions above 0, and those excursions have lengths. Okay? And as I've said, they're roughly coming out in an order which is not strictly decreasing, but which is sort of stochastically decreasing, because that comes from this sort of big drift that we've got here in the process. Okay? So what I now want to do is think about putting those excursions in decreasing order of length. Okay? So the length of those excursions, that's this list C here. Okay? And the corresponding S's are the number of Poisson points falling in the corresponding excursions. Okay, so if I can manage to wipe off a bit of board, I'll write that down. Okay, so you can see that there is genuinely a kind of relationship between the numbers of points falling in the excursions and how long they are. At least intuitively, it feels like a longer excursion maybe has more points falling in it. Okay, so then C1, C2, and so on is the ordered sequence of excursion lengths. Of r lambda, and S1, S2, and so on are the numbers of Poisson points falling in the corresponding excursions. Okay, so is that reasonably clear? Now is the moment to ask, if not. Okay, so here the excursion length, so I've got lots and lots of them, of course, because this is a Brownian type process. So, I've got lots and lots of tiny excursions. But one thing that is a consequence really of this negative drift is that there is a longest excursion somewhere. Okay? And there's a second longest excursion. So there's no shortest excursion, but there's a longest one. Okay, and so this is a theorem. This is not completely evident. I'm just sort of waving my hands at it at the moment, that you can actually put them in decreasing order. Okay, so that's an operation that makes sense. Okay, and given that, you can then find the numbers of Poisson points falling in each of those corresponding excursions, and so for the ith largest excursion, SI is the number of Poisson points falling within that excursion. The key is that I'm allowed to do this reordering. And, what might you worry about? Sort of things wandering off arbitrarily far to the right and me losing track of the biggest things potentially. And that doesn't happen. What do I mean length? I just mean length. So exactly. So how long is the interval that it? Because it has this. Okay. So this drift may be initially positive, but it will eventually the t squared on 2 is going to beat the lambda t. Okay. Okay. Thank you for the questions. So, firstly, this picture should remind you of something by now. Okay. So I've got kind of excursions of random lengths, but I've got a picture which can be split up into excursions which have got points in them, and that's really the same picture that we had over there, like excursions with points in them. So what I hope to argue by the end of this lecture is that these little things here are little random copies of those. Okay? And so we can actually put these results together at the end of the day in order to come up with a metric space scaling limit for the whole graph. Okay, so we need to do a little bit of work before we can get there. So the first thing we need to do is think about what's the discrete thing that's going to converge to this picture. Okay? And probably by now it's not going to surprise you to know that I'm going to do a depth first walk. So that's basically the tool I've been using for pretty much most of this course. So what am I going to do? I'm going to do the same sort of exploration that we did in the connected graph setting, but I'm going to concatenate the depth first walks that go with different components. Okay, so in order to do that, I need an exploration order. Okay, so I'm again going to do exactly what I did in the context of a connected graph. I'm always going to explore from the lowest labeled vertex within a component. And I'm going to use the labels to give me a sort of left-right ordering among the children of a particular vertex. Right, so that's always going to tell me where I need to explore next. I use the labels. So that's exactly as we had in the connected setting. What do I do when I reach the end of a component? I now look for the component in the graph that has the lowest labeled vertex within it that's remaining. Okay? And I'm going to use that as a next place to start exploring. So remember that the property of the Łukasiewicz path is, okay, it moves around and eventually it lands up at -1. So it has to go through 0 because it can make steps of magnitude at most 1 downwards. Okay. So rather than starting again at 0, I'm going to start at -1 now. Right? So the second component, I'm going to start my Łukasiewicz path not from 0 but from -1. Okay. And so then I've got some Łukasiewicz path that goes here, and I end up at -2 at the end of that component. And so this has the nice property that I'm encoding component sizes as these lengths of excursions above past minima. Okay? So that should feel very much like the picture that I rubbed off here, where I had the sort of running minimum. Okay, so in this picture, the running minimum is going to count how many components I've fully explored. Okay, so when the running minimum is -1, I've explored completely the first component, and I'm in general somewhere in the exploration of the second. So let me write some of that down. Okay, so I'm going to use the vertex labels again to give an exploration order. So glue together the depth first walks of the components, where we start the exploration of the kth component from where? From so minus k minus 1. Okay. Okay, so the effect, or the upshot, is we encode the size of the kth component in this exploration order as the amount of time taken from, let's say, tau minus k minus 1. So this is the first hitting time of minus k minus 1 to the first hitting time of minus k. Okay, so these are first hitting times. So tau minus I is the first hitting time of minus I for this big depth first walk that I'm defining. Is that clear? Okay, so this is quite a nice way of exploring the components and encoding their sizes as some functional of this stochastic process. Okay, so let's be clear. So the depth first walk is now starting from 0. And again, I'm just doing the same thing. And this is very convenient because this thing really is basically a version of a random walk. So what am I doing? I'm just summing up again from n minus 1, I equals 0 to n minus 1. So dn of I minus 1, where dn of I is now the number of children in the depth first exploration of the vertex vi, where v0, v1, v2, and so on are just the vertices in the order that I visit them in this depth first exploration. Okay, so I'm starting from the vertex labelled 1. Okay, so I ask how many children does it have? Okay, so my first increment is number of children minus 1. I go to the second thing, suppose this is the lowest label, let's say it's 2, just for definiteness. I ask how many children does it have that I haven't yet seen? Okay, and I put number of children minus 1 into this process. And I just keep going as before. And because once I've explored the first component I'm at minus 1, I don't need to do anything to start from minus 1. That's where I'm naturally starting off anyway. And I just add on again, number of children minus 1, and I keep going. And when I hit minus 2, that's the end of the second component, and so on and so forth. Okay, so what's different here? These guys are no longer IID. Right? So the first one is a binomial n minus 1, roughly 1 on n. Okay, or 1 on n plus lambda on n to the 4/3. But the second one, well, I've taken out of contention these 3 vertices here. Okay, so it's stochastically a little bit smaller. I've got fewer places I can connect to. So it's a binomial with a slightly smaller first coordinate. Okay, and so on and so forth. So these guys are sort of stochastically gradually getting a little bit smaller and smaller over time. Okay, and actually that's what this drift in the limit process is capturing. It's capturing this fact that over time the vertex degrees are sort of getting smaller and smaller stochastically. Okay, so how am I doing for time? Okay, 45 minutes in. Okay, so let me state the theorem that we're really going to use here. Oh, I need one more bit of notation. So remember that surplus edges, so those are edges which go from whichever vertex I'm currently exploring to something that's sitting on the stack at the same time. Okay? So actually, as I do my exploration, I can kind of generate the surplus edges as I go, right? I'm testing 2 things. So I first say, let me generate my children. Okay, so that's one binomial random variable. And then, well, I know how many things there are sitting on the stack. So let me just simultaneously ask, how many edges have I got to vertices on the stack? Right? And again, because I've got this nice independent structure between my edges, if I know the size of the stack, that's just a nice independent binomial quantity, right? So if I'm conditioning on the size of the stack, I've then just got a binomial size of stack p, number of edges to the stack. Okay? So I can keep track of that as a point process. So nn of I, or nn of k, let's say to be, no, I've done I here. K there. Sorry, get there in the end. So nn of k. So this is the number of surplus edges encountered by step k. Okay, so at each step, I'm just adding on a new binomial number to this, okay, given what the stack is. Okay. So then the key to everything is the following convergence theorem. Okay, so jointly in the Skorohod space, so jointly in, so I'm now thinking about R plus R. So what have I got? So let me write this down and then talk you through it. So this is my depth first walk. And what this result says is that if I rescale the time by n to the 2/3 and the space by n to the 1/3, then what I get is convergence in distribution to this Brownian motion with a parabolic drift. And if I also look in the same time scale at the number of surplus edges that I've encountered, that's converging in distribution to this inhomogeneous Poisson point process. Okay. So this is counting the number of points that I've encountered in the limit, okay? And this is doing the analogous thing in the discrete setting. Okay. So why is n to the 2/3 the right thing to be doing here? Well, at least once we know that the right size scaling for the big components is n to the 2/3, and those big components are being encoded as excursion lengths, then we need to rescale by the n to the 2/3 in order to see the right thing. Okay, and then the n to the 1/3 here, this is just the Brownian scaling. If I'm rescaling time by n to the 2/3, I need to rescale space by n to the 1/3 if I want to see something Brownian coming out in the limit. Okay, and this again, all I've done is I've sped up time. Right, I haven't done any other rescaling. And I am indeed getting just an integer valued process at the end of the day. Okay, so I'm going to prove this theorem using the martingale central limit theorem. And if that's not something you've met before, if you take nothing more away from this lecture than just that, then I'm already happy. This is an incredibly powerful theorem. It's extremely useful. So if this thing were just a simple random walk with IID increments, right, this would be straightforward. This would just be Donska's theorem. But I've got this sort of complicated, you know, my distribution of my jump sizes is sort of changing over time. Okay, so my limit process has kind of two components, right? It's got a Brownian part and it's got a drift part. Okay, so my approach is going to be, I need to separate those two things out. I need to show that the sort of, once I've got rid of the drift, the thing that I obtain converges in distribution to a Brownian motion, and I need to show that the drift is also doing the right thing in the limit. Okay, so let's have a bit of notation first. So I'm going to define In of k to be minus the running infimum. I think this is probably not terribly consistent with what I've done in other bits of the notes, but I think this is going to be convenient. So what is this? So this is minus the running infimum, so this is a positive quantity, right? So this is just counting the number of components that I've fully explored before time k. Okay, so when I take the vertex vk, so the kth vertex that I visit starting from 0 when I count, so I'm at vk, I take it off the front of the stack, how many other things are there sitting on the stack? Right, so this is size of stack minus 1. Okay, so that should be the depth first walk, except remembering I'm now starting the exploration of a component from some negative point. Right, so I need to add that negative point back on, and that's precisely this ik. Okay, so when I take, so vi off the top of the stack, there are, so xn of I plus in of I, other vertices sitting on the stack. Okay. And additionally, other vertices that I've already visited. Okay, so suppose I condition on these values of xn and in. So then there are possible edges from this vertex vi to how many other possible places? Well, I've got n minus I minus 1. So the I vertices I've already visited, vi. And then I also want to exclude the things that are sitting on the stack. Okay, so that's another xn I minus in I. Okay, so possible vertices I haven't yet seen. So in particular, if I allow myself to know the information xn of I plus in of I, the distribution of this dni is simply binomial with this first coordinate, or parameter. And of course, every edge is independently present with my probability p, which was 1 on n plus lambda on n to the 4/3. Okay, so that's the distribution of this out degree of the vertex vi in this kind of spanning forest of the graph that I'm in the process of exploring. Okay, so I think it's going to be convenient at this point to have some notation for the natural filtration of my process x. Okay, so let's let, so I don't have to keep saying given this. So let's let fkn be the natural filtration, so the sigma algebra generated by xn of I for I between 0 and k. Right, notice that this contains the information about the running infimum in particular. Okay. So what I want to do is think about what's the conditional expectation of, well, an increment of my process. So what happens at time k, I add on, sorry, this was k minus 1. So dn k minus 1 minus I. So let me think about this at point I. So if I think about the conditional expectation of that random variable, what am I getting? Well, you can see that there's a term that's giving me a 1 here, which is basically this n times 1 on n, right? And that I'm subtracting off here, right? So what I want is all of the rest of the product of these two terms here. Okay, so if I try to do this blind, I'll just get it wrong. So let me copy it off my paper. So I've got an n on lambda to the 1/3 minus an I plus 1 on n. And then I get a term which is minus xni plus ini divided by n. And then I've got some final term which looks like this. This is all divided by n to the 4/3. Okay, so my claim is that this is the bit that is going to show up in the limit, and that everything else is actually just going to be negligible when I send n to infinity. So this is kind of, this bit's all junk. Okay, that's an error term. And this is the thing that's going to give me my plus lambda t minus t squared on 2 here. Okay, you can kind of see how that's working. This is sort of linear in time. This is constant. So when I integrate it, I'm going to get constant times t minus something quadratic here. Okay, so that's the basic idea. Okay, so in order to do this formally, I need to split my process x up properly into two different bits, one of which will capture the drift, and the other of which will capture sort of the stochastic variation. So I've got this process x, which I want to try and understand the scaling of. Okay, so I'm going to split it up according to its Doob-Meyer decomposition. So I want to split it up into a martingale part and a sort of predictable process. So let's let, so mn of k be, so the sum from I equals 0 to k minus 1 of so xn I plus 1 minus xn I. So this is an increment of my process, and I'm going to subtract off the conditional expectation of this increment given what I knew at time I. Okay, right. And so that's a construction which is always going to give you a nice martingale. Okay, so this is martingale. Okay, and the bit that I've subtracted off here is going to represent my sort of drift. Okay, so let me rewrite this whole thing here. These just telescopes, so I may as well think about this as xn of k minus the sum of these conditional expectations here. Okay, and I'm going to call this process, without the minus sign, so an of k. So in particular, if I just rearrange this expression, I've split my process x into a martingale part and a bit that's going to represent the drift. Okay. So similarly, I want to do something kind of similar to this for the square of the increments. So let's define Qn of k to be, so the sum from I equals 0 to k minus 1 of, so the square of one of my martingale increments, okay, minus, well, the corresponding expectation, which here I'm going to write as a conditional variance. Okay, probably got enough brackets now. Okay, so this is again a martingale. For very similar reasons. So let me give myself some notation. let's take this part here. So the sum from 0 to k minus 1 of, so this variance, or conditional variance of an increment of my process x given fi and I. Okay, so let me immediately write down an expression for this. This all looks a little bit abstract, but we do actually have kind of explicit expressions for this. So we know that an increment of our process has just got a binomial distribution, right? So its conditional variance is just np 1 minus p for the appropriate n's and p's. Okay, so this is n minus I minus 1 minus xni minus ini times, so this is my p, 4/3, and then 1 minus p. Okay, so it's a bit long to write down, but there's nothing too scary in that, hopefully. Okay, so then mnk squared is equal to qn of k plus vn of k. Okay. So lots of definitions so far. So let me take a step back and say what we're doing here. So I think it's quite useful to keep in mind Levy's characterization of a Brownian motion. So Levy's characterization says that a Brownian motion is the unique continuous local martingale, which is such that when I square it and subtract t, that's again giving me a local martingale. Okay, and that t, that's the quadratic variation of the Brownian motion. So the point is that this quantity here is going to play the role of the quadratic variation for this process here, right? So this is the thing that when I subtract it off mnk squared gives me a martingale, okay? And similarly, here I've got a decomposition into a thing which I'm going to deal with separately and a martingale. And my claim is that assuming that this martingale is well enough behaved, if its quadratic variation process is converging in probability to t, then this must be converging in distribution to a Brownian motion. So obviously I've got a little bit of rescaling to do here, because for the moment I'm dealing with processes which are taking integer values. Okay, so if I want convergence to a Brownian motion, I'm going to need to do some rescaling. But roughly the idea is that I want to show that the quadratic variation of this thing is converging to t. Okay. So I'm going to skip one sort of technical part which I've put in detail in the notes, which is a proof of the fact that, well, this thing really is an error term. Okay, so here I think it's clear. So the i's that we're going to be looking at are on the order of n to the 2/3, right? So this is n to the 2/3 divided by n to the 2/3, so that's an n to the 2/3 term, 1 on n to the 2/3 term, whereas here we're looking at things which are 1 on n to the 1/3, right? So these guys are clearly going to dominate this first bit, okay? If this is, I'm about to show order n to the 1/3 at most, then again, that's going to be like 1 on n here. That will go away. And if, again, this is like n to the 1/3 on the top, then this is 1 on n to the 2/3 rather than 1 on n to the 3rd. So hopefully that's a kind of, it's straightforward to see why, assuming I can show that if I look at the largest modulus of my process x between times 0 and tn to the 2/3. So as long as that's tight on the order of n to the 1/3, then everything in this junk bit is of smaller order than the stuff at the start. Okay, so this really will be the thing that's dominating. Okay, so see the notes for that. It's a nice little optional stopping argument. Okay, so if we know that, then it becomes relatively straightforward to see, so let's call this star. So then, from star, if I think about this process A here, which is just what I get when I sum that up over n to the 2/3 steps, well, that's giving me something which is such that the following holds. If I rescale by n to the minus the third, time by n to the 2/3, and then I need to subtract off what I want to be my limit drift, then that whole thing, if I take the sup over s less than or equal to t, then that's just converging in probability to 0. As n goes to infinity. Okay, so that's just making formal what I said here. If I integrate this bit, that's giving me lambda t divided by, well, lambda times, so I get n to the 2/3 times t, divide by 1/3 here, n to the 1/3 here, and another n to the 1/3 here, and that really is giving me a lambda t, and so on and so forth. Okay, so just summing up these first bits here is going to give me a sort of Riemann sum approximation just to this quantity here. Okay, and similarly, if I look at this quantity here, well, what I'm now asserting is that this thing is tiny. Okay, so really all that's going on here is the rest, and if you multiply that all up, what you see is that when you rescale, so maybe let me move this. There's nothing I want to get rid of. Okay, what I'm going to do is I'm going to rub off everything except the expectation down there. So again, if I sort of multiply this thing out and I'm a little bit careful with the error terms, what you end up with is that this process Vn in the correct time and space scaling, okay, so this is looking like n to the minus 2/3, a sum from I equals 1 to the floor of Tn to the 2/3 of something which is, well, 1 plus a thing which is OP of n to the minus a third. Okay? So the point is that here, when I sum up this 1, what I'm basically getting is just a t. Okay? And then this thing, even when I sum over these error terms, is going to vanish as n goes to infinity. Okay? So this whole thing really is converging in probability to t. Okay, so we're now in good shape to apply the martingale central limit theorem, which is theorem 9.2 in the notes if you want to look at the statement. So it has two conditions. There's this one, that this thing that makes my squared increments into a martingale is indeed converging in probability to t. And then I need a condition on, let's say, the large jumps of the martingale. Right? So I don't want it to be the case that the large jumps are contributing in the limit. Okay, so I want this thing to be sort of the sort of random walk type process where big jumps are not dominating in the sum. Okay? And in order to do that, I need something called the Lindeberg condition. So that's given explicitly in theorem 9.2 in the notes. So I want to apply the martingale central limit theorem to Mn. I've already sorted the drift out. Okay, so this is the only bit that really needs to be done. So this is telling me that the drift of my process is tending to the right thing. So if I can show that the martingale is converging in distribution to a Brownian motion, I'm done, because I've got everything else already there on the board. Okay, so in order to do this, I need to check the Lindeberg condition. Okay. Right, so maybe now I can get rid of the bit more stuff here. Okay, so we said that the jumps of this process are kind of getting stochastically smaller, or the steps of my process xn are kind of getting stochastically smaller over time. So this is sometimes gets referred to as the attrition of points effect. I've got less and less space for my graph to expand out into, right? And so at each step, I'm getting sort of on average slightly fewer connections to the outside world. Okay. And that gives me nice stochastic comparisons, actually. So it tells me that, you know, my biggest vertex degree is really stochastically right back at the start. Okay. So let me observe. If I think about this random variable dn of I, so conditionally on the information about the process up until time I, dn of I is stochastically bounded above by some random variable b, which is just binomial with parameters n and 1 on n plus lambda on n to the 4/3. All right, so I've got a uniform stochastic upper bound on my numbers of children. Okay, at least given this quantity. So if I think about a large step size in my martingale, so what does that correspond to? That corresponds to a large value of dni minus its conditional expectation. So if I want to think about the possibility of this guy getting large, right, so this is the modulus of a step of my martingale. Okay. So if I want to think about that being large on the scale of n to the 1/3, right? So remember, I'm rescaling space by n to the 1/3, right? So this is a big contribution from a particular step of my process. Okay, the only way to achieve that is if this quantity is big, because this mean here is roughly 1. Right? It's, well, 1 plus lambda on n to the 1/3. Okay? So it's certainly at most 2, say. Okay? And so in particular, the only way to achieve this event is by having dni itself be bigger than epsilon n to the 1/3. So what I want to argue is that this is an event that occurs with pretty tiny probability. Right? This is stochastically bounded above by a binomial random variable that has mean basically 1. Right? So this is you know, something that's just very, very unlikely to occur. So in particular, if I think about a value of I that's between t n to the 2/3 minus 1 and 0, then it's the case that if I think about squaring this increment, right, so remember this is a condition on the martingale, so I need to think about increments squared. Okay. When I square, I'm going to rescale by n to the minus 2/3 rather than by n to the minus 1/3. Okay, and I'm worried about the case where this guy is big in the sense of being bigger than epsilon n to the 1/3. Okay. So I've got a nice stochastic upper bound. I can bound this above by n to the minus 2/3 times the expectation of, well, we've said, how is this event of getting big achieved? It's achieved by dn itself being large. Okay, and dn is bounded above stochastically by this b, so I can bound this whole thing above by the expectation of b squared on the event that b is bigger than epsilon n to the 3rd. Okay. And the point is, well, I can just do an easy bound here. This is bounded above, say, by the third moment, divided by epsilon n to the third, by basically Markov's inequality. Okay. And so in particular, this is certainly, again, this is a binomial random variable with mean basically 1, right? So it's certainly got a finite third moment. Okay. Well, let's say it's order 1 in n. Okay. So hence, if I think about summing up over all the steps of my martingale, so the thing that we need to be sure goes to 0 is this quantity. So I've got t n to the 2/3 minus 1. The expectation of my martingale step squared on the event where the step is big in magnitude. And I want this conditional on fni. Okay. Yep, okay, I think we're good. Okay, so the point is that this whole thing, so here I've got something which is order 1 on n. Okay, so I'm adding up into the 2/3 quantities which were order 1 on n and dividing by n to the minus 2/3. And so in particular, this whole thing is big O of n to the minus 1/3. So it's certainly going to 0. Okay, so I've not got big contributions from particular kind of summands here, right? Really, everything is just getting nicely kind of evened out. Okay, so in particular, this tells us that we've got our martingale part converging to a Brownian motion by the martingale central limit theorem. We've got the drift part converging to lambda t minus t squared on 2. And so if I sum those two things together, I'm getting the convergence that I needed. So let me write that over here. So by the martingale CLT, we have that n to the minus 3rd suitably rescaled martingale is converging in distribution to my Brownian motion. And we already saw that the rescaled drift part was converging, well, uniformly in probability, but so certainly in distribution, to lambda t minus t squared on 2. Okay, and so if I sum these two things up, I'm just getting convergence in distribution to what I wanted. Okay, so in particular, for the whole process xn, I indeed get convergence in distribution to w lambda. Okay. So there's one little extra step, which is that I sort of want the sum of x and its running minimum to converge to the reflected process. Okay, but that's just an application of the continuous mapping theorem. Okay. So if you like, that's the running size of the stack. So the reflected process. Okay, so I'm not going to go through the proof for the surplus edges simply because I don't really have time to do everything here, but I've put that in details in the notes. And again, it's kind of a martingale argument, right? So you're looking for convergence to a Poisson process, and the way the argument goes is to check that the compensator does the right thing. And because you've got an increasing process, you then just need to check again that you're not making sort of large jumps anywhere in order to get convergence to a Poisson point process. So again, that's nice sort of stochastic analytic methods. So something I'd like to emphasize here is that we're trying to understand that most discrete of objects, a random graph, okay? And what we're using are the tools of stochastic analysis here. So a priori, something that we think about as sort of continuous kind of methods, okay? And there's a really nice, these are really powerful tools when applied to this discrete setting. And sort of the ingredients that we need are a sort of Markovian exploration. So this XN process, this is a Markovian encoding of the graph as I explore it. And once you've got that available to you, you can then use this kind of technology in order to give convergence to nice continuum stochastic processes. And then you can think about what the limit objects must mean. Okay, so that's kind of the message of this lecture. So I sort of owe you a little bit of an explanation of how we get from this to the theorem about the convergence of the component sizes and surpluses. Okay, so we've already a little bit discussed this question of whether we can order the excursion lengths in the limit process. So what do I need in order to get convergence to those ordered component sizes? Well, I also need to know that the components of the discrete process can't wander off to plus infinity. Okay? And something that's really useful for that is, again, that we're exploring this graph not in a very uniform way, if you think about it. So what am I doing? I'm starting exploring from the component labeled 1. All right? So in particular, what does that do? That picks out a size-biased component from among all the components available in the graph. Right? I'm more likely to fall in a bigger component. And once I've taken that component away, the second one, wherever the next lowest label is sitting, is again in a size-biased component from among the rest. So although I'm not looking at the largest among the components remaining, I'm looking at something which is biased to be among the bigger ones. Okay? And that size biasing is precisely the sort of technical tool that we need to say that, well, things can't wander off to infinity because I'm looking at them in this sort of size-biased order. Okay, so that's a very hand-wavy way of saying that we can get to the answer. Okay, so I've put quite a lot of stuff in the notes about this limiting process. So in particular, I've talked about its excursion theory, and I've given a proof of the fact that these limiting excursion lengths are square summable. But I think that's something that it's maybe a bit too technical to go through sensibly in the lectures. But those of you in particular who've seen the excursion theory for a Brownian motion, it's a sort of relatively straightforward adaptation of some of that material in order to see some properties of this limit process. Okay, so maybe I've got sort of 2 minutes, maybe 3, and I just want to say a few words about how we get from these component sizes and surpluses to a scaling limit for the whole graph. And I'm just going to sort of say a few words here, and at the beginning of the next lecture I'll try to write something a bit more sensible down. Okay, let me at least write down the sort of key lemma. Right? This is a nice simple discrete lemma about the properties of the Erdős-Rényi random graph. So I think this is lemma 7.4 in the notes. Okay, so let me take some subset of my vertex set. Okay, so I've got n vertices. So let's condition on the event that that's the vertex set of a connected component. So conditionally on V being a connected component of GNP. And it's also conditional on its surplus. So with S surplus edges, then, well, that component is a uniform random connected graph on that vertex set with surplus S. Okay. So, okay, I haven't any longer got vertices labelled by 1 up to n. They're labelled by whatever the labels in V are, but that doesn't matter. Those are just labels. Okay? So this is in particular a component of the Eder-Srini graph that has a particular surplus. It's just a copy of one of those things. Okay? All right. And moreover, if V1 up to Vk are the vertex sets of a collection of k different connected components, the graphs on those vertex sets are independent of one another. So conditionally independent. So in other words, I can think of creating this graph as a sort of two-step procedure, right? I can first say, what are the sizes of the components and their surpluses? And then, well, I can come along with sort of new independent randomness, and I can generate the components. Okay? And each of those components, as long as we're looking at surpluses which are sort of finite rather than diverging in n, well, then we're in good shape to apply that theorem there. So roughly what I'm going to do at the beginning of next time is show you that once I've got this theorem of Aldous on the component sizes and surpluses, we can really just plug into each one of those components the result that's over on the little board to say, well, actually we get convergence of the whole thing with these little metric spaces corresponding to each of the connected components. Okay, so I'll try and write that down sensibly at the start of next time, and I'll stop there. Thank you.